but Dr. Freeman is a woman of many hats. She serves as a SERC Research Council member with particular focus in the trusted systems area, in addition to being a SERC principal investigator. Additionally, Dr. Freeman serves as the director of Hume Center's Intelligent Systems Lab and the assistant dean for research in the College of Science, as well as a research associate professor in the Department of Statistics at Virginia Tech. Dr. Freeman also serves as part of the executive leadership team for the Acquisition Innovation Research Center. And with that, I turn it over to you to introduce our esteemed speaker in the talk.
Thanks, Mimi, and thanks everyone for joining us today. It is my pleasure and honor to introduce my friend and colleague, Dr. Darryl Ahner, and thank him for kicking off our T&E series. We'll be following up with information on the additional talks in our series in the future, which will include representatives from the DoD and the Joint AI Center. So Dr. Darryl Ahner is the director of the Scientific Test and Analysis Techniques Center of Excellence, and was instrumental, and I enjoyed working with him on standing this up. But he was instrumental in shaping its operational concept and directing kind of the initial visions for the STAT COE. He is also a professor of operations research at the Air Force Institute of Technology. As the director of the STAT COE, he is responsible for executing the center's mission to provide independent advice and assistance to major acquisition programs in the application of scientific tests and analysis techniques in the development of their T&E strategies and plans. The center also conducts externally funded applied STAT research, provides STAT education, and develops best practices and case studies. And if you're not already on their listserv for distribution, I highly recommend you get on it. Lots of good best practices that they send out there. Darryl is a licensed professional engineer in the Commonwealth of Virginia. He has also written over 50 technical articles. His bio claims that he's given over 70 technical presentations. I have to imagine, given the number that I've collaborated with him on, it's far more than 70. And has also been key in establishing technical working groups across the department. He has been a faculty member at the Air Force Institute of Technology since 2010, and his research emphasizes optimization of test and evaluation, reliability, stochastic models, simulation, and military operations research. So a great speaker to kick off our test and evaluation series. He is a member of the Institute for Operations Research and Management Sciences, Informs, and an International Test and Evaluation Association. He's an active member of MORS as well, the Military Operations Research Society, and is most recently serving as Vice President for Professional Development and Vice President on the Executive Committee. Dr. Ahner is a 1990 graduate of the United States Military Academy at West Point. He retired from the Army in 2012, and during his time in the military, he was awarded the Legion of Merit and a Special Act Award for leading modeling and simulation and analytics. In addition, he has received another Legion of Merit and a Meritorious Service Medal, 3 awards, and an Army Commendation Medal. His academic studies include Rensselaer Polytechnic Institute, where he earned an MS in Applied Mathematics and an MS in Operations Research and Statistics, and Boston University, where he earned his PhD in Systems Engineering as a Draper Fellow. Dr. Ahner, thank you for joining us today, and the floor is yours.
Thanks, Laura, and thank you, Mimi and Kara and the rest of the SERC team. Laura is definitely a leader in the test and evaluation world and beyond, so I'm very honored to have been asked to talk today on this subject matter. So I am the director of the STAT COE, and we are funded out of OSD R&E, more specifically receiving our funding from the director, Mr. Collins, out of the Office of the Director for Developmental Test Evaluation Assessments. That being said, anything I say today is of my opinion and not official policy of the department. However, we are aligned very heavily in our thought process on how to drive test and evaluation forward. So as mentioned by Laura, almost 10 years ago now, we were asked to stand up a center that focused like a laser beam on test planning in the follow-on data analytics. And what I mean by that is once we determine that we want to conduct the test, we look at how can we efficiently and effectively plan for that test and then others execute that test, and then we get heavily involved with the follow-on data analytics. And just as Laura said, we provide that direct support to the major acquisition program managers, and that's where our baseline funding from DTE&A comes into play, as well as accepting other funding streams to drive the state of test and evaluation forward, as well as provide short courses on the STAT process, reliability growth, and those types of things. We like to think that we've done a fairly good job at doing so and have grown significantly over the years, such that in 2017, the Department of Homeland Security approached us to perform the same types of test planning and follow-on data analytics for their programs, as well as developing best practices and delivering course material. So STAT, what is this scientific test and analysis techniques? Well, the idea is 10 years ago, we were talking design of experiments, and design of experiments in and of itself is not adequate unless it's applied within a process. And so the STAT are those methods and processes by which we apply design of experiments, but also look at observational studies, reliability growth, software testing, and the like. The whole idea behind STAT is to focus our test efforts around the things that impose most risk. For instance, the new use of old technology, new technology, or the interactions of our system with other systems, the interfaces. And so with that, we've for about the last 7 years been part of both on the developmental test side and the operational test side, have been part of the policy, the DoD I-5000 and now the 5000.89 as they split it out, in which STAT must be applied for both DT and OT. So what does that mean? Well, why are we doing this? And you'll see some parallels as I talk about this, some parallels that go right along with digital engineering, right? We're trying to increase the agility, the speed by which we're developing systems and getting them to market. In our case, our market is deployment to the soldiers, sailors, airmen, and Marines, and the DHS folks now that we're trying to support. We're trying to understand the innovation. We don't want folks to just say innovation, but how do we measure it? How do we ensure that innovation is real and can be applied within our material acquisition process? And then we've always, within the test and evaluation community, been interested in quality, ensuring quality throughout the development of a system and the final delivery of that system. And so, not surprisingly, these three things come into play, not just in test, but also in digital engineering. So we often get the question, well, how much should we test? And I alluded to testing where risk is most prevalent, right? So that risk can be associated with systems engineering decisions, or that risk can be associated with acquisition decisions. And so we use STAT where, as it shows here, we want to achieve efficiency. We want to have effective testing. We want to be able to inform decisions. We want programs to own their technical baseline. And ultimately, we want to achieve the desired performance. And if not, we want to be able to apply STAT to characterize what is going wrong with a system. And I have some examples of that I can talk about later, where things weren't performing as desired. We were able to characterize that performance, which led to systems engineering corrections to that performance, which achieved a better system in the end. Well, again, I said we apply STAT for individual test sequences or test events. Well, what tells us what that test sequence or test event is? Well, currently we use a developmental evaluation framework. We're going more towards a unified evaluation framework, but in essence, it's conducted where the system performance is uncertain, and the evaluation framework also looks at where lack of system performance creates the most risk to the mission. And so that part isn't changing even within digital engineering. Just the way we go about doing test and evaluation might change as we look at digital engineering, or we look at the different acquisition pathways within DoD. And so it's going, I would argue digital engineering and test in general is going the way of Admiral Meyer here, where it says You come up with a sequential test strategy, you test a little, you know a lot. So I mentioned this stat, and I mentioned statistics, but statistics can't be applied to a program in a vacuum. Just doesn't work. The statistical pixie dust cannot be spread across the test plan and magically we understand what the system does. We need to focus it, and we focus that through the stat process. And so this very much aligns with some statistical giants efforts that have been out there, like Doug Montgomery from Arizona State University, where we have the plan, design, execute, and analyze phase. But we very much drill down to make it a test engineering process to say, here's the process we need to go to develop a very good test plan in order to achieve the objectives, which we're going to define up front. So we need to understand the requirements. We need to understand where stat can be applied. And then we need to work with the program, the engineers within that program, to determine those objectives, to determine what exactly we're measuring to meet those objectives, what we can vary within the test to better understand that. And then you'll see some DOE type language like select factors and identify constraints. But it's interesting to some that planning phase within our stat process typically takes us about 80% of our time working with individual programs so that they own their test process, they have those efficient, effective testing, and we're testing the right thing. Once we do that, with the advent of statistical software, the design portion with a well-trained stat expert becomes that much easier. So the planning actually is the linchpin to coming up with good designs. And those good designs are achieved through many statistical software packages that are typically in my shop. I typically have advanced degree folks with at least a master's and many with a PhD, who are and also a very large retired military folks that we have at least 10 years of acquisition experience per stat expert that can do all this, get to that design, be very well trained in that software, use that software to come up with that design, and work with those test organizations within the program construct to then execute the test. So those test organizations execute the test very well within their labs and their test ranges. And then we get heavily involved with the data analytics. And so then you'll see a lot of statistical language put in there, but it's very much a clear-cut engineering process that we work within the program and the larger test community to then have feedback so that we come up with sequential tests and getting away from this concept about just having stovepipe tests that don't learn from the previous test. And so that's what we're working for in general with the stat process. So I maintain a list of what are our challenges for complex systems. So let's face it, the complexity of our acquisition systems has increased dramatically over the last 20 years. We now refer to them as cyber physical systems, or at least the National Academy of Science and Engineering does, because they almost all of them have a software component. And even though there's a mechanical component, there's always a software component. Many of them are only performing a part of a mission or a kill chain, and there's interconnected mission and kill chains that need to be accounted for within our testing. And so that efficient and effective test within that environment becomes a challenge. Stat gets us there. The reliability testing continues to be a point of emphasis. Just read any DOT&E report, any annual report there. DevSecOps, what does testing look like within DevSecOps? We've done a lot of work in that area, which I won't share today just due to time. And as we're testing more in a virtual environment, how do we know we can trust those models? So we're going to talk a little bit today about validation of modeling and simulation and how we might get there so that not only is there a yardstick for our developers to understand how good their models and simulations need to be to make decisions, but that we can also inform decision makers on what risk they're taking by looking at the analysis of an experiment conducted with that model, a test, if you will. And so that they're informed with how much risk am I really taking on whereas we're getting away from just the, is it validated or is it not validated for its intended use? Well, how well is it validated? Then the fifth one there, the test information integration within digital engineering, I'll be talking more about model-based systems engineering. How do we tie in with that? Because that's here and it's here to stay. And then the others there you'll see with the test ranges, the interoperability and the cyber, which are also on our challenge list. So the challenges of testing are many. And so how are we going to address them and take care of them? I'm going to talk about some of them today. So let's talk about digital engineering. So if we listen to digital engineering folks, that we're going to leverage models, right? So if we look at the DoD digital engineering strategy, it says the model is the authoritative source of truth. So we're going to leverage that model, and I would argue that it's not a model, it's models, plural, that to accelerate, to virtualize, to continuously update, and we're going to reuse those models and data as we get product improvement programs and the like. And so that's what we're trying to achieve with digital engineering. I would argue we've been doing that for the last 10 years with STAT to try to realize some of those same things, albeit less with models. And now we're looking at how can we supercharge digital engineering to do the same thing, but through STAT with digital engineering. And so the last bullet is key. The model validity and readiness are critical. Because if we can't trust our models, if our models aren't accurate, then we're going to have a challenge. We need those models that lie within that digital thread of digital engineering, all those buzzwords strapped together there, that they all need to be consistent and they need to build upon one another. And I'm going to talk about test and evaluation and how that plays a role within digital engineering to achieve some of those desired accelerate, virtualize, continuously update and reuse aspects of digital engineering. So here we go. Again, I'm showing you the STAT process. I will say we've used the STAT process heavily within the physical world. Over the last couple of years, we've applied it greatly to the live fire in the software world. But we're moving beyond physical testing, and we need to understand what it means to test within a virtual environment. STAT won't be just used to come up with a test plan within the virtual environment. I would argue STAT is needed in order to develop those validation schemes to see how well our models are actually performing and how consistent are they and how do they hold up to truth. So just for a very simple example, I'm looking at testing within a digital thread. So, and we've actually had prototype programs where we've applied this. So we've concurrently, for example, with our program, our pilot program that we've done internally, a multi-million-dollar effort, we've concurrently developed an AFSIM mission level model along with a model-based systems engineering model and help them maintain consistency. We leveraged some work that MITRE had done and simplified it a little bit to ensure that we could pass the parameters back and forth between the operational simulation and the MBSC model. We greatly took advantage of a very large group of experts, which were also funded to get the SME and engineering insight to not just come up with a good test plan, but also to inform our MBSE efforts and our AFSIM development efforts. And what we were able to do is we were able to develop within Cameo a model-based systems engineer of our system, a design of our system based upon a very clear architecture up front, and implement that within our AFSIM. And through our AFSIM model, we were able to use STAT to explore the space, not given a ConOps by the customer up front, be able to explore what is the state of the possible and what do engineering trade-offs enable within the system, and ultimately do a cost versus capability analysis of that system, and ultimately inform how that system should be built and moving forward with the acquisition of that system. Well, that just doesn't happen one pass through. That's a sequence of development and testing, and allows us to really move with an additional thread things forward, but also only move it forward that fast because we had the very insightful designs that we were doing with our scientific tests and analysis techniques, space covering, and those types of things. Laura, did you have something?
Yeah, there's a question in the chat that I think is relevant to what you were talking about now and on the last slide, where you emphasize that model validity is critical. And so you've just given an example of where you were able to kind of meet that validity criteria for MBSC models. There's lots of different types of models out there. And the question from Carol is, has any analysis been done to state how often models are right or right in the critical areas to drive T&E?
So good question. So I had a very good conversation with some operational test and evaluation folks, and again, this is just a snapshot of their comments. Was they were very concerned with most models that they've seen used in operational test and evaluation were subject matter expert validated. In other words, they showed them to the subject matter expert, and he or she said, looks good. And so the question is, what kind of risk is the decision maker taking on if it's just a subject matter expert saying looks good? Are they asked before you do the analysis, or are they asked just to look at the analysis results and say looks good? So that's a big difference, right? If we get it a priori, then there's some independent validity to it. But if we get it after they look at the results, then it might be biased a little bit. And you can come into that. Also, have we asked the subject matter expert whether the results looked good for that intended use across the full range of possibilities, or just at a single point? And so their concerns at the very highest level of DOT&E was that there wasn't a good validation scheme for OT. Now, if it's not there for OT, then it probably hasn't bubbled up a lot from DT. And while I am sure, just like with design of experiments and STAT, when we started 10 years ago, there's pockets of excellence across DoD. I'm sure there's pockets of excellence, but it hasn't taken an enterprise move forward to how are we going to actually use these models within digital engineering. And it's more than just MBSE, and I'll get to that here in a slide or two.
All right, we got two more questions for you before I let you push on. So related to that, how important is model pedigree in ensuring model validity?
So it goes back to trust, right? We're not going to talk trust in AI. Now we're going to talk trust in modeling, right? And so a lot of it has to do with trust. And what I'm going to talk about here in a little bit, I'm going to throw the concept of model readiness at you, and we're going to talk about how much can you trust that model. What is the validation based upon? What's the referent that you're basing that trust upon? And have you validated that model against that? You know, we can build models from the ground up using physics, but those physics interact. Those physics take on. So the pilot program I was talking about was a space system. So you can imagine we were looking at what is on each satellite, what's the communication scheme, all those types of things to look at a satellite constellation. And we had to build that trust from the ground up. So what we ended up doing is going to the experts in each of those technologies to make sure that that piece of technology, that physics for that particular phenomenology was correct. But who do I go to ensure that the integration of all that technology is how it really is in the real world? And that's where I would argue we make our best guess. We base it upon the composability of the MBSE. We relate that composability over to the MBSE or to the AFSIM model, and we gain some trust through that. But the ultimate trust is, here's our best guess. Let's run a few real life things, and hey, we were right. Or if we weren't right, can we figure out where we weren't right? And so a long drawn out answer to the trust question of our models.
Well, I think you maybe just answered or related answer, or sort of answered Frank's question on how was the MBSE model used to support test planning? And then we've had one more pop up, but then I'll let you go back to talk.
Yeah. So so what we were doing with the stat process in the planning phase was sitting down in the program with the larger test community, but also forcing in a stat working group, the systems engineers, the contractor engineers into the room to truly understand the system under test. Well, you see where I'm going with that. What does model-based systems engineer, good model-based systems engineer give us? It gives us a very good understanding of that system under test. It's not replacing bringing those people in, but it's giving us a cheat, right? We should have a decent understanding of what that model-based system engineering is giving us, that cameo model in our case, before we bring the experts in, because testers typically aren't experts on every single system under test. And we need to learn from our engineering colleagues and be able to apply that knowledge in our test planning. The ideal is to take the range and the factors that are important from model-based systems engineering and be able to directly port them into our test plan would be the ideal case. It's always a little messier than that.
Great. And one final one that really directly relates to this slide is, what is the purpose of the MBSC model in the middle of the graphic compared to the one on the left, which maybe defines the architecture from George?
On this particular slide, is he talking?
Yeah, so the MBSC engineering model you sit in the middle, how does that relate to the MBSC model on the left-hand side that's kind of feeding into the test planning?
So I think there's an interconnectedness of models. Thank you for letting me go for the next slide. And so when we look at the digital engineering and the digital threads, again, I don't think it's like the DoD strategy says a model. I think it's models. And all these models come to bear, right? The MCAD, the ECAD, those are things that us actual engineers do when we're designing a system. But we also do the MATLAB models, and I just think of them as MATLAB models, but the physics level model that is, I mean, engineering is applied science, right? And so those engineering models capture that applied science for that particular phenomenology that we're engineering at the time. And so those all link heavily into the systems engineering model, and they're in the middle. But I think you also have to understand that there's test data and empirical models that are related, the cost model, the operational analysis model. And the thing that always gets left out, and we always think of this, in my opinion, too late in the game, is that sustainment model. And what MBSC also allows us to do is to bring that sustainment model thinking more forward in the process. And so that's where I think the MBSC model fits in general. So hopefully that got to at least partly answer that question, Laura.
Yeah, great. Thank you.
So some key takeaways here is STAT applies to both physical and simulated environments. You don't just stop test planning just because you're in a model environment. There may be less sources of error, but you still want to take a rigorous approach to understand the exploration versus the exploitation. Exploration to say, are we covering every place where this system's actually going to perform? Exploitation being drilling down into where we're going to perform those things more often, or where interesting things are occurring that we need to better understand. And so planning is critical in each one of those. And this here just breaks out some thoughts on physical testing versus simulation testing. And the idea is that I believe that testing within a digital environment sequentially will better inform the systems engineering process, but it will also better inform the downstream test in a physical environment, such that we can say if our assumptions and our models are valid up to that point, that we can drive on. But it does create a risk. Digital engineering does create a risk that once we do the live testing, if it doesn't match up, that's the curse of being a tester is, oh my God, testing stopped the program. No, testing didn't stop the program. Testing just highlighted where the program went awry. Now we need to circle up and fix some of those key issues before we move forward further. And so that's how I see the physical testing versus the simulation testing trade-off here. And so, for instance, here we have just an idea of what real system data is across the top. So it's a regression model, and we get these predictor profiles. So as altitude, airspeed, downrange, cross-range things change on that slide, you can see that we get a trend with an uncertainty bound, and the uncertainty bound is not extremely large, but it's larger than the bound below, because in a modeling world, sometimes we tend to not adequately show what uncertainties can inject into the system. That may or may not be true, but in this case, it is true, just from this example. And you can see if we've done our digital environment development there on the bottom correctly, then it aligns, at least trend-wise, and an impact of those various factors changing in our testing with the actual real system above. And so that's just one way of thinking about it. Does it align both in a mean sense, but also in a variability sense as we're looking at our models and we're comparing it to the real world? Does it give us enough insight to be able to go quick early, correct some of those issues, understand the system a little bit better, than to go to live testing a little bit later on? We've basically decreased the risk of finding bad things in live testing, which is a different way of thinking of digital engineering than most of you have probably thought about it in the past. And so just like we look at structure, behavior, requirements, and parametrics in digital engineering in the MBSC world, those are the types of things we also have to capture in our mission level models. But it's also the types of things we should be thinking about when we're coming up with our test plans to ensure that they're as thorough as possible. So in this way, I think MBSC is a great move forward in testing, because we're going to think about the system in a more complete way. And then just from a SysML taxonomy breakdown, again, just looking at the previous slide in a little different taxonomy, things that we need to think about as we're going about testing and as we're going about modeling with the mission level models, to ensure that these models within our digital thread are consistent and they better inform the virtual testing that then leads to just, again, I'm very cautious of using this word, but kind of a validation testing in the real world to say, yes, our models were in fact good enough to give us the insight that we had a good system or not, and then adjust as required.
All right, so I'm looking ahead on your slides. I can't get my video off quick enough. And I think this is a good point to ask Frank's most recent question, because it relates to MBSC models. So in STAT, is there a step or steps to use MBSC models to aid in describing what I like to call the system of analysis?
So we are diligently working with that in the engineering directorate in R&E, and more specifically at DTE&A. I know I've been working with the MITRE folks, my MITRE colleagues, who are pushing the ball forward with this as part of the larger group to include the STAT COE and other FFRDCs, and they're doing great work in being able to define, okay, how do we do that? How do we, instead of stovepiping MBSC and stovepiping digital engineering, how do we truly get them to feed off of each other, work together early on to understand the system, to understand the risk that we're doing, to understand how well those models are representing the real world, and be able to move faster. Again, it goes to that concept of the agility, right, that I had early on, the agility, the innovation, the quality. That's where I think they align very well. And if they work together early on, which we're trying to put those guidebooks and whatnot in place, then I think we can move faster and understand more.
Yep. So I'll just say what I heard you say is in the very beginning, like as we shape the STAT process, having MBSC incorporated into that definition of the system is where it's needed.
Yeah, I mean, I think you have to have that model consistency, and what the STAT process does is allows you to exercise those models to understand them better and give you that insight and analysis. Right. So, you know, again, how does digital engineering support T&E? Kind of putting it backwards, right? Not how T&E supports digital engineering, but how does digital engineering support T&E? Well, we have those models where we can do a lot more test points than we can do in the real world, and we can reuse those models and data for like systems and also within a system as we go through product improvement programs. We virtualize T&E to reduce the testing costs, and then we continuously update those models and data to better understand the system, processes, procedures, logistics, right? That idea of having a digital thread that actually, you know, eventually leads to a digital twin. If you have all those models in place and they're accurate, depends what your definition of a digital twin is, because there is a couple out there, but all these things are kind of a precursor to being able to achieve that digital twin, to have digital telemetry feed back into a digital thread through the life of a program to truly understand what's going on there. And I haven't talked about things like design for tests, so we can measure things we care about and those types of things. Those are important as well, but you get the sense here where, you know, as we partner with GBSD, as we partner with space and ISR systems, as we partner with the ET7 now and the advanced pilot trainer system, that they're pushing the digital engineering barriers forward on how they're doing their programs. And there's a lot of lessons learned about how we can do this, move faster, and have a greater understanding. So it is about having that greater understanding earlier on with that mission context. And that's why I put mission level simulations along with model-based systems engineering to occur concurrently so that they can feed off of each other. And so finally, so how do we do this? How do we end up with models that we can reliably use for testing? And so folks have looked at things like model readiness levels in the past. We call ours a model readiness level to say, why do we want a model readiness level? Well, we want a model readiness level so developers can have a yardstick by which they can measure the goodness of their models and their simulations. And it allows them to create a requirement for funding to improve their models if needed, and understands what is the appropriate use and the appropriate scope of their models. But it also allows for decision makers to understand the risk that they're taking, given a model readiness level. What is the risk that they're taking in making a decision based upon that model, whether it's the program manager or whether it's higher up in the chain at OSD level. So they need to have some kind of yardstick to measure where their models and simulations are, and what kind of, and on the decision side, what kind of risk are they taking using these models and making decisions based upon that. And so in order to accomplish this, I've challenged my team to ensure that the model readiness level that we're developing is usable, that is comprehensive, and that it has the mathematical rigor and consistency to go along with that. And so it needs to be usable by the practitioner. You need to be able to tell the practitioner what right looks like. And that's why I think this model readiness level approach gives us that ecosystem to start looking at this, start understanding where the funding needs are and what these models can actually be used for. It is a work in progress. There has been work done along these lines in the past, which I think we should leverage, we should refine, and we should get this. I think the model readiness level concept is a key enabler for digital engineering to be successful. And so the dimensions of that matter in a model readiness level, if we really want it to be rigorous, is we need to have the fidelity. And so what I mean by fidelity is the accuracy, resolution, repeatability, and consistency. We need to understand what is the referent that we're using. So is it just the subject matter expert? Is it a legacy system? Is it system, is it actually data from a representative prototype? What is that referent authority? Because the referent matters. How much we can trust it is directly mapped to the goodness of the referent. And then the scope is, it quantifies the degree to which the model and the referent represent the same system. So I had mentioned using a similar system. Well, that's not going to be as good as using a representative prototype of the actual system that just needs to be refined. And so we think of the model readiness levels along the lines of fidelity, authority, and scope in order to develop models that are usable. And so I mentioned fidelity. And so here's a nice pictorial of what resolution, accuracy, repeatability, and consistency look like. And so you can see on the resolution slide there, it's the amount of uncertainty in observed values due to the computational limitations of the model. It's rounding errors, precision of numerical calculations, precision of measurements, those types of things. Whereas the accuracy is the difference between what the model should produce and what it actually produces. And so you can see, are you hitting the bullseye on whatever measure of performance you're looking at? So don't think of this as just dropping bombs, but is actually just looking at whatever measure of performance you're looking at. And so are there tendencies to underestimate or overestimate results? That all ties within our definition of accuracy. And then repeatability speaks for itself as the variability in the simulation across runs with the same input conditions should yield within the error bounds similar results. And then the consistency, which is the limiting behavior of modeling and simulation as resolution increases and our reputation increase trends towards the expected result. And so the consistency of the results that you're getting. And so we break it down very theoretical. Sorry, we are in a research forum, right? But we break it down into, if we're going to look at model readiness levels, we need to look at fidelity in that way. Then we need to look at referent authority. And this is a nominal authority level there to the right. We're working with the greater community to say, what should those authority levels be? And if we can come up with the different levels of authority, then we can start mapping those into the model readiness levels. For those of you who worked with 6.1 through 6.3 research, the technology readiness levels do the same thing for different technologies. We're looking at doing the same for models and simulations. And then finally, scope quantifies the degree to which the model and referent represent the same system. As testers, we've often gotten things on the test range where we say, oh, we've tested something like this before, so therefore we're going to use the same approach for this item. This is kind of the same thought to say, how much does the model and the referent actually represent the same system? And so, for instance, why do we want to test design in a simulated world versus the operational world? Because we have limitations, right? I just got done taking part in a National Academy of Science study for test ranges, and we have all these limiting factors on our ranges, right? We have encroachment issues. We have electromagnetic issues. We have all those types of issues, which, yes, we want to test in those environments, but when we go into the simulated world, we can much more easily look at the combination in the whole space in which we want to test. And so that's also a big thing we don't want to, a big understanding we don't want folks to lose when we're going into a virtual world, as long as that virtual world is representative. And so here you can see in the lower right, we can only look at live data in a small part of the operational envelope where the white dots there, versus on the left where we look at a virtual world, we can look just about anywhere as long as we believe that the intended use of our model is being adhered to, and that range is a viable representation of what the real system might do. And so that's the result. That's the main point of this slide. Laura.
Yeah, So I've been holding on some questions because I saw you were going to tackle them in your upcoming slides, but I think now might be a good time to pop in with a few questions that we've had coming up in the chat. So there was one question directly related to this slide on kind of what data you'll need. And so Philip has asked, is it understood that there may be an increase in testing required upfront to facilitate model validation? And kind of in the context of this slide and what is needed for model validation, want to throw that over to you.
So again, not talking for the department, I really believe that back when we talked technology readiness levels, that a technology readiness level should not be allowed to advance without an accompanying model of what that technology is able to perform. And that might be too big of an ask, but that would serve the digital engineering advancement and reaching across the valley of death, right, of technology development to actually implementation with an acquisition system. That might be a panacea to be able to look at that and have the digital engineering build that bridge through that modeling, through that testing, experimentation, if I may, back in the labs, right? Because they're more willing to call it experimentation. We, in the acquisition world, call it testing, but it still has the same roots. And so, yes, I believe that if we are to do digital engineering right, it does require, as that technology is being developed, more modeling and model validation earlier on, which requires testing in a virtual world and testing on the, in less realistic environments to understand the physics, capturing those physics within our models, capturing those engineering requirements within our Cameo developments, and moving that forward. But I think what that does is that's going to increase the agility, so that we can get the innovation and the agility moving and the quality at the end of the process. So circling all the way back to that innovation, agility, quality, I think that's what it gets us. And so I think it's a smaller scope of testing, but more often in a sequential matter that builds on our knowledge, rather than 10, 20 years ago when our testing looks very stovepiped, right? I think it demands that we look at more of a sequential approach, along with what Admiral Meyer's quote was there.
And related to that, and your comment on the sequential approach is driving me to this next question. How do you see model readiness levels within the BV&A context?
So we are working with MSC up at OSD. I'm not saying they've bought into the model readiness level, but they're definitely intrigued. They're intrigued because they're looking for, there's a lot of, the slides I took out of this presentation were the validation background, right? There's documents out there that have some good definitions and some good validation in, but I think the idea of validated or not validated, even for its intended use, has to go the way of a bigger ecosystem where we're looking at, okay, validated, but at what level? How much can we trust it? If we can trust it the whole lot, maybe that takes our live testing needs down to a minimum. Again, not talking for the department, but if those models aren't validated, maybe our testing demand for live testing looks the same as it is today until we can capture enough data to validate the models for future programs that are similar. And so it's not going to be an overnight, click of my fingers to say, okay, we're done. We can now do digital engineering. I do think there's an on-ramp to be able to do that. But I think in the long run, we're going to learn a lot more in a virtual environment that leads to smaller live tests, and maybe even test events that don't just focus on one system, but we have test events where instead of testing one system, we're testing the multi-domain operation aspect of a system, because we're confident in our digital engineering environment. And now let's do the test event that's more focused on the multi-domain operation and the integration with other systems, as opposed to that singular system. But again, I think that's a long road ahead, but I think we can get there.
So a few more questions on model readiness levels. So you put the question got asked before your slide on technology readiness levels came up, but the question was, should they follow that? But the piece that maybe it would ask you to pause on is, how would they differ? What needs to be different in a model readiness level from a technology readiness level?
So technology readiness is focusing on one technology, and it's a linear path. It never goes back, right? I would argue model readiness can actually go back, right? We can say we're going to have a product improvement program or a subsystem enhancement to a system, and that model readiness for that one might actually go back a level or two, because we just don't have the data to understand exactly how that's going to perform in that particular environment without validating. But the other thing we want to be able to do in real live systems, and it kind of goes back to that design for test concept, not design for test just in development, but design for test across the entire operational life of that system, in order to understand, okay, our models are validated because we have the real live data, and also feeds back into the digital twin to understand what the logistics needs of that system are. And so that's a whole different way of thinking that's begun, but obviously in the legacy systems, I can't tell you how many times we ran into an issue with a subsystem where we wanted to measure something, but because the system's not designed to measure that, well, we'll just drill a hole. Well, if you drill a hole, you fundamentally change the system. So you have to be careful not to inject more problems than what you're trying to test to figure out. And so those issues become, we really need to have a digital engineering environment. And as we're growing, there's going to be growing pains.
Great. Speaking of data, a question on model readiness levels. Is there any empirical research underway to validate the MRL concept?
So we are embarking in a very mathematical, rigorous approach to how we foresee model readiness. We are also learning from the efforts in the past, but we do need to make sure that they meet those three criteria: the usability, the comprehensiveness, the other one that I can't remember, sorry, but back on my slides. We think that that's a requirement. If it doesn't do that, then people aren't going to use it, and it's not going to have its intended effect of being a yardstick for improving our models and being able to communicate our requirements for improved models to the decision maker. And it's also not going to be the yardstick for the decision maker to understand the risks that they're taking, whether they're doing systems engineering decisions or acquisition level decisions.
One more before I let you go back and get to your final slide. But how is validation and verification done for data-driven models? Are there some techniques that are similar to the MBSC model?
So we're not just looking at validation of MBSC models. The model readiness level actually takes on the mission level models as well. And if you're a model and simulation person, you understand that you cannot simulate reality. The runtimes will kill you. And at some point, it's actually you can get empirical models that are developed either from running a simulation, and you don't actually you use a lower level simulation to develop an empirical model, and then the empirical model just uses the response surface up into the model runs so that they run a lot faster. Or you can use live testing to create empirical models and use those empirical models within your modeling and simulation. A lot of modeling, if we go way back, well, I just used a lookup table. Well, no, you didn't just use a lookup table. You use a simplification of an empirical model. Why don't you just use the empirical model? And as an aside, one way of looking at validating models is, in fact, to create an empirical model of the simulation and the empirical model of the real world and see how closely they match. And they don't have to match 1 and 1. Maybe they just match in their trending and not in their absolute value. Maybe they don't match in their, maybe they match in their first moment. So they do exactly match, but they don't match in their second moment, the uncertainty that's involved. And so those are things that are actively being looked at as well.
Excellent. I'll turn it back over to you, given the time to close out your.
Okay. So the takeaways is I look at digital engineering as providing the potential for the increased innovation, agility, and quality. I'll just add here that, I have a hard time talking about test and evaluation of autonomous systems without looking at digital engineering, because I think the digital engineering is the enabler for complex cyber physical systems, but it's also an enabler for those complex adaptive systems, although there's additional challenges which I didn't talk about today. I think STAT complements digital engineering in 2 ways. You have to have the rigorous and defensible model validation. Without that, we can't really get the benefits of digital engineering and of the digital engineering thread and get to the digital twin in many cases that we want to. And we do that by efficient and effective test designs through STAT. On the model readiness level front, they really need to be usable, comprehensive, and have mathematical rigor and consistency. One of the things we ensured with our pilot program was when we did the concurrent development of our MBSC model and our AFSIM model, we looked at how do we ensure consistency between the two and got to the point where the MBSC tool actually generated the runs for the AFSIM models. The AFSIM model did an optimization of the engineering design and then fed those parameters back to the MBSC model. So we streamlined that a little bit. I'm not going to say we're the first ones to do that because MITRE had done it before. We just had done our own implementation. And I think there's a lot of goodness in doing that. The model readiness levels will facilitate these continuous model improvements and allow decision makers to really benefit from our digital engineering approach. And then finally, test and evaluation is about determining what do we need to test and ensuring the rigorous test planning that feeds effective evaluation. So evaluation is really where it's at. Are we able to do developmental mission assurance for DT and be able to have that innovation, agility, and quality that we want? And so I can't claim they snuck in this is the way this time because they did it my last briefing, but I left it there so that it seemed to play well before. So with that, I'll open it up to more questions if other folks have questions. Appreciate your time, and I hope that this was a value use of the last hour of your time.
Excellent. Well, thank you, Darryl, for your time. And there are a few more questions left, but I think we'll be able to answer them through the chat as needed. So thank you, everyone, for your questions and very active engagement in this briefing, and Darryl for your time pulling this together and sharing these insights with us. Mimi, do you have anything to close us out?
Just on the next slide, some dates to keep in mind and just a preview of the upcoming talks. But just to save the date for our annual event happening November 2nd, 3rd, and 4th, fingers crossed that we'll be able to have our in-person event introducing the Acquisition Innovation Research Center on November 2nd in DC. Either way, there's a virtual option for this, so we hope you'll be able to join us for this, as well as the next test and evaluation talks within the series. Our tentative date, I believe, is October 27th for the next talk, but we'll be providing the information for this talk, the recording, once it's available in a few days. Everybody who registered for this talk will receive the announcement on that, as well as more information on our upcoming talks. But just echoing, thank you so much for this fantastic presentation, and Laura for incorporating the questions in. We'll be sure to follow up with the questions and include the responses in our send out. But with that, I think that closes us out. Thanks everyone for joining us.